Good day, everybody. Before I jump into the problem here, I'm going to write down some notation that I'm not that familiar with, but I'm going to write it down. I think this will get the point across. This is a cyclic structure here on the left-hand side. Notice how they say cycle because the B cycles up to there. The C, and everything just cycles over if you look at what's going on here. And they call that cyclic. It's not symmetric. And that's sometimes easy to maybe get that confused, but I think the notation I've seen goes like this. You just put cyclic down here as the lower index of the summation, cyclic. And then here our general structure is just x squared over x plus y. And I'm not sure how to convey it. I don't know if you put it out to the side, but it's cyclic in the variables A, B, C, and D. Right? And this is actually another way to write this. Now, again, this may be a slight departure from what the standard notation is. They may even abbreviate this. Anyway, this right here suggests four terms if you just think about where everything has to go. A, B, C, and D all have to end up here at the top, right? And that's what happened, A, B, C, and D. And you can see it's just kind of cool. I kind of like it. All right, so this symbol is another name for this. Now we have the variables A, B, and C, and they're positive real numbers. I think that's important here, although I'm not 100% sure why. But the R plus just means the positive real numbers. And the initial condition here is A plus B plus C plus D is equal to 1. Okay. Now we want to show that this left-hand side is greater than or equal to the right-hand side. And I'm just going to use Cauchy-Schwarz. You only have equality if the ratios are going to be equal to each other, and it's unless it's 1/4 plus 1/4 plus 1/4 plus 1/4, they're not. Okay, so what we're going to end up with is just strictly greater when we're done with this, based on this equality condition. Now, something that's important based on the given condition, and this is something you'd have to spend some time with before you knew that this was important, so I'm not motivating it particularly well. But notice that all of this is equal to 2 times A plus B plus C plus D. But that initial condition tells us that this is equal to 2. Okay? Now, y'all, the rest of this, I tried to be as clear as I can here. I didn't want to show a whole lot of work because it just gets kind of clumsy. But what I did do when I applied the Cauchy inequality, that is this object right here. Now, this is fun stuff. Usually you see this in the square root form here, where this is an inner product, less than or equal to the product of the magnitudes of the vectors. This is another way to write it with everything just squared, But anyway, I made these assignments, which are fairly natural if you look at the problem statement, okay? So A1, you can just see what I've done here, okay? I basically broke the thing up to where A1 is the numerator and B1 is it contains the denominator plus A in the numerator. So it's not real clear, but if you've seen Cauchy-Schwarz, you can understand why these assignments take place. Now you'll notice here, and I apologize, I wanted to keep it all in one line. I think it's better, but I got a red object here and a green object on the left and right hand sides of the equality. Notice that would be this part right here would be just, let me just write it directly up here. This whole part right here would be the red. It's hard for me to switch colors in this interface, so I wish I could write red. I could, but it's just still kind of clumsy. But this is red, and this is the green part. And if you take a look at this assignment, you can see why. I'm not going to try to run through each step, okay? But it works out rather nicely, actually. This left-hand side would be this red object based on these substitutions that you see. And this right-hand green side would be this right-hand side here, okay? And yeah, you can see the 2 down there. And again, I couldn't make it any bigger. Sorry about that. But when you simplify all this, it's all, not much happens here other than you get this, you replace this with what it's equal to 2 times the sum, okay? And then this next step is a little bit of algebra. You divide through 2 times this sum. If you divide it over here, and it's positive, so you don't change the sense of inequality, you get this statement here, okay? But notice that this is just equal to A plus, this is just equal to 1/2. That's fairly neat, I think. So that's the proof. really not much happened there other than just knowing how to. It was pretty much just a direct application of Cauchy-Schwarz. You didn't have to do anything else or any other comparisons, inequality comparisons. It all just fell right out. So we know that this, and this is what we're looking for. We proved this. So let me write QED. Okay, so QED, quandam est demonstrandum. Okay, and then I have a concrete example here if you have a hollow feeling about all this. Okay, I arbitrarily chose, not arbitrarily, let's come along here and try to keep everything on the screen. Now, y'all, you'll notice that, and I chose this to add up to 1, which makes it fit this problem statement. A plus B plus C, and you guys can verify, plus D is equal to 1. Spent quite a bit of time trying to get them close to each other, sort of, or roughly all of these are about the same size if you look at the magnitudes here. They're not too far apart, like 1/5 is what, 3/11 and 12/55 are pretty close to each other in numerical value, you know. And so they're not too far apart. And but when you sum all that up, you can verify it's equal to 1, okay? And so when you substitute, I wrote it in here for you, y'all. And again, I left out quite a bit of the work. In fact, almost all of it. Finding the common denominator is a pain here. I let technology verify it. I did it wrong. I got to the sum. It's a big pain to do the common denominator here for these numbers. It's doable. It would be a good exercise, but it's error prone, and I made an error the first time I did it, so I just trusted the technology. But notice that we got this number here that's greater than 1/2, and it was pretty tight. You know, it's not too much bigger than 1/2, right? How do they do that? With a little, there's a symbol for just barely greater than. But anyway, that's kind of fun. Now, let's take a look at where just this first term, just so you'll trust me. This very first term here would be, you got we're dealing with A and B, right? So it would be 1/5 squared. And I did do, this one's not too hard to do because it's just a simple unit fraction. But then that would be over A plus B, which is 1/5. And I won't simplify it. I'm just going to tell you where it came from. You know, it's kind of tedious arithmetic. We don't want to waste too much time on the video on that. But that's 12 over 55. Okay, and again, it's a fairly easy verify, I think. Let's see, you can almost see it happening here. This would be equal to 1 over 25. Okay, over, and I'm just doing the first one. So y'all, let's see, 11, this would be 11 times, so you would get 23 over 55 is what I'm getting, folks, right? You need to multiply this by 11, so 11 times 1 is 11 plus 12, so you get 23 over 55. And you guys, you can see when you invert and multiply, this is that, okay? You can almost see it. You turn the 55 over, what do you get? 11 over 5. So you get 11 over 5 times 23, which is 11 over 150. And it gets harder. This very last term is a pain right here, you know, because you're dealing, they're just larger numbers, and it's a little messier to do it. It's not super hard, but just, I would say the hardest part would be finding the greatest common, the least common denominator. And I'm not even sure if this is the least common denominator, actually. It probably is. I don't know, though. It's just kind of a messy exercise. But anyway, we know that the proof this is strong evidence that there's no mistakes on the proof right here, because we did get a pretty tight sum here, you know. And I think if these numbers are more spread out and they still add up to 1, it's not quite as tight in here as far as, but this is very, very close, you know, to 1/2 as it stands. So anyway, y'all, I liked it a lot. And there's people that do the Olympiad guys. They actually can think in this cyclic notation. Some of these guys like Evan Chin, and there's the guys that are practiced IMO types, you know, who are authors and stuff. They actually can think. They can look at the cyclic notation and just reason through it. And handle it as an operational object, so to speak. Here, I'm still not there. I have to look at it, but they've gotten so good at it. I guess it's just because they do all these math competitions. I don't know if I'd ever get there, but to recognize this, and you can write down some properties of cyclic sums, which are different than symmetric sums. Okay. So anyway, fun stuff. New notation for me. Hope you enjoyed the problem. Let me know what you thought.